Warm regards to all. I am very delighted to talk about my research background in this platform. After the completion of my post graduation, I joined a battery department and worked there for about 2.5 years. After that, in July 2022, I joined with Dr. Beena S, Associate Professor, Department of Chemistry, Amrita Vishwavidyapeetham, Kerala, India, for pursuing my PhD. The prime focus of my study is the fabrication of electrochemical sensor for the detection of analytes belonging to different domains. And my thesis title is that development of functionalized metal oxides and sulfates integrated electrochemical sensors, a comprehensive approach for the detection of biomolecules, food dye, and water pollutants. Talking precisely about my PhD work, my thesis is primarily consisting of the fabrication of 5 electrochemical sensors. We try to bring in innovation and try to improve the sensor performance by introducing novel materials of surface modifiers for the fabrication of working electrode. The materials were characterized with techniques such as XRD, HPS, Raman spectra, IR spectroscopy, FECM, EDAX, BET, and HRTM. In detail, analyze their morphological and structural attributes. The electrochemical studies were performed by using cyclic voltammetry, differential pulse voltammetry, linear sweep voltammetry, and electrochemical impedance spectroscopic techniques. In addition to my thesis works, I have also fabricated 5 more electrochemical sensors, and 2 of them were during my international internship tenure. Talking in detail about my thesis work. In work 1, we have developed an electrochemical sensor for the detection of cysteamine, a decarboxylated byproduct of amino acid cysteine cysteamine. The working electrode is fabricated with surface engineered iron oxide nanoparticle here. The surface of iron oxide is modified with functional groups of terephthalic acid for improved selectivity and sensitivity towards cysteamine. This developed sensor is used for the quantification of cysteamine and achieved great result with both glassy carbon electrode and screen printed electrode. The linear range of the sensor is exceptionally broad and higher than the previous reported literature. The practical efficiency of the sensor is also analyzed with real samples such as human urine. This revealed good results. The synthesis procedure of surface engineered iron oxide and working electrode fabrication is depicted here. The results of DPV studies of linear range investigation and real sample study are also given in here. Moving on to the second work, where we discuss about the electrochemical quantification of homocysteine. Homocysteine is a vital amino acid in human body, and an abnormal rise can be an indication of disorders such as Parkinson's disease, Alzheimer's disease, and so on. Here, we introduce a novel nanocomposite such as iron molybdate iron sulfide nanocomposite to fabricate the working electrode. The sensor achieved exceptional linear range spanning from 13 micromolar to 9061 micromolar. The practical efficiency of the sensor also verified with real samples such as human urine as well as blood serum. The synthesis of composite is depicted here. The result of linear range investigation is also given here. The values starting from the normal blood range value gives hope for the future biomedical application. The result of real sample investigation are also included in here. And we are also in the middle of processing this work as an Indian patent. Moving on to the next work, where an electrochemical detection of food dye such as brilliant blue is discussed. For that, a composite incorporating molybdenum disulfide and polyvinyl pyrrolidone is used. The sheet-like structure resulted after the integration of PVP in MOS2 increased the electronic properties of the sensor and delivered better performance than the previously reported literatures discussing the detection of brilliant blue. The practical reliability of the sensor verified with various real samples and achieved satisfactory results. In the next work, a multi-metal metal oxide composite which has a mesoporous texture is developed and employed for the quantification of a water pollutant, that is catechol. This particular sensor achieved an extensive linear range spanning from 0.8 to 8296 micromolar, surpassing all the electrochemical sensors reported so far discussing the detection of catechol. The real sample studies also performed with wastewater from chemical industries and achieved good results. We are also in the middle of patenting this particular work. In the next work, the electrochemical quantification of 4-nitrophenol, another water pollutant, is discussed using a composite such as cerium sulfide, iron sulfide. These sensors also derived results superior than any other electrochemical sensors reported so far discussing the detection of 4-nitrophenol. That's all about my thesis works. Moving on to the other works. Here we have developed an electrochemical sensor utilizing a novel composite such as molybdenum telluride and functionalized carbon nanofibers and employed it for the detection of an oxidative stress biomarker in human body such as 4-nitroquinoline and oxide. This sensor also derived exceptional electrochemical properties in terms of linear range, selectivity, sensitivity, and all as compared to existing literature reports. The practical application of the sensor is performed with human urine and blood serum and recorded impressive results. As you can see, the synthesis procedure of the composite and the linear range study are also given in here. Moving on to the next, here an electrochemical sensor for the detection of 4-nitrotoluene is developed using MOO3 and CO2 composite and yielded remarkable results as compared to the existing electrochemical sensor for the 4-nitrotoluene detection. In addition to all this, I have also developed sensors for the detection of tryptamine, adenosine, and guanine. For all this works, pencil graphite electrode served as the working electrode. For the detection of tryptamine, I tried to bring in polyorthodiphenyl diamine film on the electrode surface through electropolymerization technique. Moving on to the next work, where the electrochemical detection of adenosine is studied using a polythiourea modified pencil electrode. The real sample studies performed with human blood serum and achieved exceptional results. The sensor proposed achieved a broad linear range spanning from 0.6 micromolar to 1345 micromolar, greater than all previous studies discussing the detection of adenosine. In the next work, an electrochemical sensor for the detection of guanine is developed with 3-aminobenzoic acid modified pencil electrode. This particular sensor also achieved superior results greater than the reported literature in terms of linear range and all. So, this is all about my research experience working in sensors. I would like to work on innovative ideas and experimenting with them as well as to learn new stuff. Thank you so much.